everybody, this is going to be kind of an introductory video to solving polynomial inequalities. Okay, so in order to do this, we're actually going to revisit the concept of solving a linear inequality that you probably did when you were in algebra. I'm assuming that most people watching this video may be in like pre-calculus or calculus or something like that. So we're going to start by considering, say down here in the bottom left corner, this linear equation, this first degree polynomial equation. So we have one root, and so this is really lame, but if you were to solve this, you know, of course you get x is 4, and really the intent that I have here is this, essentially that when you graph your solution, of course, you say, okay, so I have 0, 1, 2, 3, 4. This is very, very basic, but the bottom line is we put like a dot at 4. We say, well, we can label this solution. This is x equals 4. This is our solution. Way to go. We are awesome. I guess the question I wanted to bake here is this, though. What did we do in situations in which we were dealing with linear inequalities? Those are things like greater than, less than, greater than or equal to, less than or equal to. So what if I were to switch this, say, to like less than or equal to? Of course, we would have solved this in just the same fashion, but we would have gotten the solution set, like an entire set of solutions. There would be all of the x values that are either less than 4 or equal to 4. So this was, in this case, we could say interval notation. We'd say, all right, well, we put a closed bracket here, or a closed dot, and we would shade all of these points to the left of 4, and including 4, because if we were to plug any of these back into this original inequality, it would totally solve it. So the fact of the matter is this: we're going to be solving inequalities today. This is nothing different from what we've done in the past, except for we are now dealing with like polynomial inequalities, which opens up the door to make inequalities that would necessarily be higher degree. So like second degree, third degree, fourth degree, fifth degree, you name it. So we have a method for finding the test intervals for an inequality, and this is going to make more sense as we go through it. But what I'll do is I'll just direct everybody's attention up here. We say let f of x equal, say, this polynomial, second degree, x squared minus 2x minus 3, and you notice that I've made it extremely factorable. But what I'd like to do is this: I would like to solve for all x values that would make this statement true, that our y values or our function values would be less than 0. So I'm saying, okay, so what can we plug into our function that would give us like negative outputs, negative y's, really, if you want to think about this as y. And so we have a method for doing this, but we say, okay, so really if I'm saying f of x is less than 0, well, we know f of x is just this expression right here. We're saying f of x less than 0. We're saying this less than 0. And much like we would solve, say, an inequality down here where we said like x is, you know, x minus 4 is less than or equal to 0, you know, what we would do is just solve for everything that would make this true. Solve it for like what would make x actually equal to 0, this expression actually equal to 0, excuse me. So this polynomial inequality up here, what we're going to do first is this. And you can see up here, this is step number 1, but we're going to find all zeros of the polynomial and arrange them in increasing order. That's kind of nice. But we say these are our critical values. We're going to give our solutions the name critical value this time. What are the critical values of this inequality? So basically, what we need to do is find all the zeros of this. So the zeros of x squared minus 2x minus 3, we could say, well, that factors down into x minus 3, x plus 1. And if we're finding the zeros of this, we'd say, okay, well then simply put, we'd say then negative 1 and positive 3 are these zeros. And we're going to give this a name. We call these critical values. Okay, so these are our critical values of our polynomial. Fact of the matter is this, though. We need these because what they do is, step number 2 over here, these values determine what we're going to be referring to as our test intervals. So what do you mean by test intervals? Well, I'll tell you what. If we were to now draw our number line, okay, the fact of the matter is this: we were looking for the specific intervals on our x-axis for which our function, in this case, would be negative or produce negative y values. So here's what we'll do. We'll go ahead and set ourselves up here. We say we'll put on our critical values. You know, I'll put on some extra ones here as well. 3, 4, 5, negative 5. But switching back to blue, we say, okay, so we've got a critical value here at negative 1. I'm going to put an x there for now. Because we would not know if that's either an open or a solid dot. But we say, okay, and in 3, those were our 2 critical values that we were concerned with. Now, when I say test intervals, what I can tell you is this: we can actually split our number line up into 3 separate test intervals. That is, from way out to, you know, negative infinity on the left up to negative 1, from negative 1 up to 3, and from 3 out to infinity. we're going to draw upon our knowledge of inequalities in the first place. But here's what I know. If we were to say, go back over to this original inequality on the left where we said x minus 4 is less than or equal to 0, we had shaded all of these points over here on the left, but the fact of the matter is this: that means we could plug in any point in that interval. So like, for example, x equals 0. X equals 0. If we were to put that back into the original inequality, we get minus 4 less than or equal to 0. We get 0 minus 4 is less than or equal to 0. That is, negative 4 is less than or equal to 0. But we get a true statement. This is totally a true statement. And basically what this means is this. Well, if x equals 0 works, and it's to the left of this critical value of 4, then every point left of this 4 here would work. In other words, all of these pink things that I'm kind of like designating here, those are all the values of x for which our original polynomial function was negative. So now going back up here to where we were previously, we said we had 3 intervals from negative infinity up to negative 1 to 3, and 3 out to infinity. But basically what I'm saying is we are going to do step 3 now. And step 3 says this: we're going to choose like an arbitrary x value from each interval, and we're going to test it. We're going to plug it back into the original polynomial inequality expression. But the bottom line is this: let's say we chose the x value 0 here. We say that's an easy one to plug in. X value 0, if we were to put that back into the original expression now that we had, which was x squared minus 2x minus 3 less than 0, and plug these in, the fact of the matter is this: we get 0 minus 3, we get negative 3 is less than 0, and this is indeed a true statement. But what this means is this: any x value that we choose now in this interval that I'm highlighting, any of those things, if we were to plug them back in, it would make it true. Not only am I saying it wouldn't make it true, but in this case we'd say those are all the x values that we're discovering for which our polynomial would produce negative y values. That is, our f values would be less than 0. Okay? So now we should test x values from these other intervals as well. So let's say I test, for example, we could test 4. We could plug 4 into our original polynomial expression. So we say, okay, so that would be 4 squared. Well, honestly, bottom line is this: like, we could say, what if we looked at this? And we say, well, we factored it, and this was supposed to be less than 0. If we were to put in, say, a 4 for x here and a 4 for x here, we get 4 minus 3, and that comes out to be 1, which is positive, by the way. And we say 4 plus 1, which comes out to be 5. But the bottom line is you're taking a positive times a positive, which means you get a positive. And we're saying, well, you're getting a positive number, and that's less than 0. And what we know is that's a false statement. Okay? So what we're saying is, well, if 4 is false, then the entire interval from 3 out to infinity is also false. And likewise, we could say, well, what if we chose like negative 2? We plug negative 2 into our factored expression. Our factored expression, remember, was x minus 3. So we say negative 2 minus 3. And then x plus 1, so negative 2 plus 1, and we say less than 0. In this case, we get negative 5, which is negative, that's all I care about, and then negative 1. So we get a negative times a negative. Bottom line is, negative times a negative is a positive, and a positive is not less than 0. So we'd say this interval from negative infinity up to negative 1 also fails. So we say, well, the solution set, well, that's what we're looking for in this one. The solution set to this would be negative 1 up to 3. This, and I don't say, this is not the point xy, negative 1 comma 3. I'm saying from negative 1 to 3, that was our interval here on our x-axis of x values that when we plugged it into our original expression, which said, x squared minus 2x minus 3 is less than 0, made it true. In other words, those were the x values for which our function was negative. Our function values were negative. So I think it'd be helpful actually if we go over here and we look at the graph of this. What I've got here is the graph of x squared minus 2x minus 3. And what we were trying to answer in the first place was, what are all the values of x that when you plug them in, your function is actually negative? And what I'm going to tell you is this: when we say our function is negative, we're saying where the y values are actually negative. So what you can see is, we have positive y values, positive, 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 and then it goes negative, 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 and negative, negative, and it goes back to being positive again. But in the first instance, we were saying, well, what are all the x values that would cause us to have negative y values? Well, you can notice right between negative 1 and 3, which, by the way, were the zeros of our original polynomial, and by the way, were our critical values of the original polynomial expression. But we're saying those would be the x values for which we would have negative y values, which is the thing we were trying to answer in the first place. So one last thing I'd like to do is this. I can actually, in this program, it's really nice, type in x squared minus 2x minus 3 less than 0. And what this is going to do is highlight all of the x values for which our function was negative. And you can really see it now that at our critical values, of course, is where we have these dotted lines. But basically we're saying that means it doesn't include -1 and positive 3. But those were all the x values that are being highlighted, for which you notice here we had negative y values. So this next example that we do here, it's just a really quick one. We're going to go through these 3 steps again. I just want people to see, well, how would you do this in general? How do you go through these steps? And we'll switch over to like a yellowish color, and that'll be easier to see here. And block this off. Whoa, that was close. So we say, all right, so I would like to find what are all the x values that would cause this statement to be true, that would cause, say, my g of x to be less than 0. I want to know, what are they? Okay, so if that means g of x is less than 0, we could say, in other words, we say x squared minus x minus 6 less than 0. So the first thing we want to do, step 1 up here, okay, we say find the zeros of this polynomial function. So we're going to factor this. And this factors down really nicely. I'm being very nice on this one. We say, okay, so minus 3, x plus 2. But you would see then that our critical values must be at the zeros of this polynomial function, which are -2 and 3. And you notice I wrote those in increasing order. So now we say, okay, so this is just going to help us determine our test intervals. So we're going to draw out our number line now. And we're going to set up our test intervals. So we say if this is 0, then we say, okay, so 1, 2, 3, there's a critical value at 3, and then 1, 2 is -2 here. There's a critical value there, 3, 4, 5. Sorry, I'm like OCD. So anyways, we say our intervals now are from way out at -infinity up to -2, -2 up to 3, and then 3 out to infinity. But we know that if something was true from each of these intervals, like if one thing is like if we plugged in now, say -3, we're just testing it. If I were to plug in -3 here, I'd get -3 minus 3 times -3 plus 2 less than 0. And we're going to know, hey, would x values in the interval from -infinity up to -2, would they make my function less than 0? So really what I'm looking at here is I got -6 times a -1, but it's not the numbers that I care about. It's the fact that I'm taking a negative times a negative, and I get something that's positive, and it's less than 0. And that's not the case. So we say the interval from -infinity up to -2, it just ain't going to work. Okay, so what if we tried, say, 0 next? 0 next. Okay, well, if I plugged in 0, it actually is easier to go up to this original expression and say, well, if I plugged in 0 for all my x values, those would go away, and I'd have -6 less than 0, which is totally true. So again, we'd say, well, if that's true, then everything between these two critical values must be true. And then as far as this last interval goes, we could plug in 4, but really I think it'd be nice to look at this graph, honestly. And just here's what we'll do. We will graph our original function and ask the question we wanted to ask again, which was, hey, x squared minus, what did we have? Minus x minus 6. Here's our function. We're saying, what are all the x values that when I plug them into my function, I get negative y values? So we're looking at the sections of our x-axis. You can see that our critical values are still -2 and 3. But what were the x values for which my function was negative? Well, it's below the x-axis between here and here. So we've already colored in this middle interval. But notice if we were to test 4 now, plug that back into our function, we get a positive y value, which is not less than 0. So we would have failed this. So again, just to illustrate this, we could say x squared minus x minus 6 less than 0. Those are all the x values that I care about because I wanted the x values in this case that caused the g of x to be less than 0. So that's just kind of a quick run through of how you would find your test intervals in the first place. Find your zeros, set up your test intervals, and then plug in a point from each test interval. And if it makes it true, we'll shade that interval. If it doesn't, then we won't shade it.